All right, so I'm going to be talking today about some research I've been working on over the past couple of months, specifically to help quantify contact tracing efficacy. And so this is all joint work that I've been doing with a group at Johns Hopkins to be able to basically help out contact tracing programs to figure out how effective they are. And so as part of that, we basically worked on a mathematical framework to help sort of think about how we could quantify this efficacy. And then we turned this into an R package to be able to actually calculate these quantities, to calculate this efficacy for specific contact tracing programs given certain parameters that you could measure as part of that program. And then we translated this into a Shiny application so that people could sort of interact with it online or on their mobile devices. And so I'm going to be telling you a little bit about kind of each of these pieces, and then I'll do a quick demonstration so you can see what the application looks like. You can find my slides at lucymcgowan.com/talk if you're interested in following along. So as I mentioned, this is joint work that I have been doing along with a group at Johns Hopkins Bloomberg School of Public Health. And so this is the team that's leading the effort here. Emily Gurley, Justin Lessler, Elizabeth Lee, and Kara Grants have all been instrumental in this process. And so here's a quick outline of where we're going. I'm going to start by talking about the model itself. And so this is the model that's kind of running behind the scenes that we came up with to help be able to quantify the efficacy of test, trace, isolate programs based on certain parameters that they could be either measuring or estimating. And then I'll talk about the R package and how to actually use the R package that we wrote to be able to implement this model. So we have a package called TTI for test, trace, isolate that can actually implement this. And then I'm going to talk about the Shiny application. I'm going to highlight a couple of key aspects, show you a little bit of code so you can see if you are interested in creating a Shiny application, how you could implement a couple of the things that I think make this app kind of cool. And then finally, I'll do a demonstration so you can see how it works. So the goal of this work, essentially, test, trace, isolate programs are an essential part of COVID-19 control. And they basically offer this targeted approach. It's a non-pharmaceutical intervention, a way that we can essentially try to limit transmission via testing, contact tracing, and isolating and quarantining people. And so effective use of these programs requires that we have some methods to estimate how their efficacy, so their current and anticipated impact. And so that's kind of what the purpose of this is sort of finding a mechanism to be able to quantify that efficacy and then being able to give programs an easy way to calculate that or estimate that themselves. Okay, so the model, the test, trace, isolate model behind the scenes. So this is kind of, I'm going to give you a simple overview of kind of the mathematics behind this, and I'm going to be talking about it kind of from a high level with a very kind of simplified version. And then in the R package, it will get into a little bit of a more complicated version that includes kind of more parameters that you might be interested in. So the work that I'm going to be talking about here is currently on medRxiv. It's under review right now. But you can find the paper if you go to this link here. And if you're interested in more details, we've got a lot more details of the mathematical framework there. So, as I've mentioned, this is a mathematical framework for estimating the effective reproductive number given a test, trace, isolate program. And so what do I mean by effective reproductive number? The reproductive number is essentially the average number of onward transmissions that an infected individual is expected to make. So, on average, how many onward transmissions do we expect each individual to make? So we can think about these three kind of exclusive compartments, these mutually exclusive compartments for people who are infected to fall into. The first would be people who are infected that are detected through testing and subsequently isolated. So that would be the detect compartment. The next compartment would contain people who are infected, but they're already in quarantine. So they are quarantined contacts of identified cases who then become infected. And then the final compartment would be people in the community that are infected, and so these would be undetected infections. So we have detected infections, infections detected in quarantine, and community infections. And so you can imagine calculating or kind of being aware of a proportion of infections in each of these compartments at a given time. So for example, we could say that 20% of the infected people are being detected via our testing, and 10% are currently in quarantine, and 70% are undetected out in the community. And so again, as a reminder, that reproductive number is the average number of onward transmissions of an infected individual is expected to make. And so you can have a reproductive number or an effective reproductive number for each of these compartments. And so, for example, people who are detected via testing, you might expect them to infect on average 2 people per infected individual. And people in quarantine maybe would infect 1 person per infected individual, whereas people just out in the community are infecting about 2.5 people on average. And the reason these are different is because you would expect that essentially once we're detecting or once people are in quarantine, they're not as likely to be infecting people kind of outside of that isolation or quarantine. And this picture, I think, sort of gives a little bit of an insight into why we would expect our detect reproductive number to be effective reproductive number to be lower, and we would expect our quarantine effective reproductive number to be even lower. And so here I've shown, this is a distribution here of transmission, and this time 0 here is when we're in time t in this top picture, and we've got folks infected here at time 0. And then this is kind of their onward transmission that you would expect, the distribution of transmission. And they get symptoms maybe on this day. So this is 1, 2, 3, 4 on day 4, 4.5 or so. And then maybe they're tested on day 5 or 6. And then by day 7, they're isolated. And so what that means is that all of these days prior in red, they could be potentially transmitting. But once they're isolated, there's a reduction in the transmissions due to case isolation. And so this area down here, folks that would have been infected here, kind of if this person were still out in the community, are no longer infected under this circumstance. And so that effective reproductive number is reduced. And then looking at the next generation, so the next generation would be an infected contact, so someone that was infected by this initial case at time t. And so this would be someone, for example, that ends up in quarantine. And so this person is infected here, and they get symptoms here, but then they're isolated. They're isolated much more quickly because they're already in quarantine. And so they kind of can very quickly be put into isolation. And then all of these folks here end up being reductions in transmission. So no one on this side of the isolation line would be getting infected. And so the infection rates go down even farther. And so another way to think about these numbers, the effective reproduction number for the detect, quarantine, and community, would be via these equations where you've got some gamma d times your reproductive number in the community and a gamma q times the reproductive number in the community. And so that gamma d, that can just come from, basically it's going to be the integral from -∞ up to td, where td is the time from symptom onset to isolation of the infectiousness distribution. And so what's happening here is essentially we're cutting off that infectiousness distribution at the time when this detected individual is isolated. So just like that picture I previously showed, we're basically only counting time in the red and we're discounting any of that time in the green. And similarly for quarantine, we would do something very similar. We've got this gamma q, where basically we're going to be taking the integral from -∞ to the time from symptom onset of the case to quarantine of the contact. And so once that contact is quarantined, they can no longer transmit any further. And so again, this is going to be that infectiousness distribution, although it would be indexed based on the symptom onset of the case, and that time will be reduced from there. So plugging those in, we can end up with values something like this, where we end up with 2, 1, and 2.5, for example. So what do we do with that? Well, we stick those, the way we deal with these mathematically is we stick these into an infection matrix. And so this is going to be, in this case, a 3x3 matrix where those R values are on the diagonal. And so among those who are detected, the R value on that diagonal is going to be 2. Those in quarantine, the R value is going to be 1. And those in the community, the R value is going to be 2.5. And so this infection matrix here basically allows us to kind of show what we would expect for onward transmissions in each of these compartments. And so if we wanted to think about new infections at time t, if we have here our proportion in each of these categories, so the proportion in our detect, in our quarantine, and in our community categories, and then we multiply it by this infection matrix, that can sort of help us see how many new infections we would expect. And so our new infections at time t could be something like 0.2, 0.1, and 0.7 times 2 times 1 times 2.5. And so then the next piece that's important is not only do we want to know how many people are going to be infected, but then we want kind of at time t plus 1 to be able to stick people into the right compartments. And so we need to know how many new infections there are going to be, and also what categories each of those infections are going to fall into. And so for the detect matrix, we've got here in the rows, these are indexed by someone who's detected, someone in quarantine, and someone in the community. So who are they infected by? And then the columns dictate where that person ends up. So they ended up detected, they ended up in quarantine, or they ended up in the community. So they ended up undetected. And so in this top corner, we have folks who are infected by someone who is detected, and then themselves end up detected. And then in the next square, we've got those infected by someone who's detected that end up in quarantine. And then we have those infected by someone who was detected that end up back in the community, so they end up not being detected. And so you can imagine that you basically are going to apply kind of different probabilities to each of these compartments to be able to determine where someone's going to land in terms of detection. And the same on the next row here, these are all going to be someone infected by someone in quarantine. And so someone infected by someone in quarantine that ends up detected, someone infected by someone in quarantine that ends up in quarantine, someone infected by someone in quarantine that ends up in the community. And then the final row is going to be those infected by someone in the community. So those that are infected by someone in the community that end up detected, those that are infected by someone in the community that end up back in the community. So this can translate into this, this matrix of probabilities, where these are sort of the specific values here. So in this top quadrant, for example, where we're trying to calculate the proportion of folks that are infected by someone who was detected and then ended up in the detected quadrant, that's going to be 1 minus this omega d times rho. And then if we're trying to determine how many people are infected by someone who's detected and then end up in quarantine, that ends up being this omega d. And someone who's infected by someone who's detected that ends up in the community will be 1 minus omega d times 1 minus rho. And so this omega d here, this is going to be the probability that a contact of a detected individual in the detect department is traced and quarantined. So someone in that detect compartment, what's the probability that they're traced and quarantined? And so that makes sense why this one would end up being that exact probability, because this quadrant represents someone infected by someone detected that ends up in quarantine, so that would be the probability there. This first quadrant is going to be 1 minus that, because an individual here does not end up in quarantine. They just end up being detected via kind of surveillance, so via just coming in to get a test. And this person over in this category also did not end up traced and quarantined. They end up just being back in the community, so that's why there's that 1 minus omega d there. And so we could put in an estimated probability there. So we could say maybe we think the probability is 0.5. And then the omega Q, that's the probability of a contact that's detected in the quarantine compartment is traced and quarantined. And so we could put in a value for that, for example, 0.7, which 1 minus that would be 0.3. And then finally, these rows here, this is going to be the probability that a community infection is detected and isolated. So how likely is someone just in the general community to be detected and isolated? And so we could say maybe 20% of people just in the general community are being detected, 20% of infections are being detected, and so we could put that in for each of those probabilities. And so the probability that someone was infected by someone who's detected and themselves ends up being detected is going to be 0.5 times 0.2. The probability that someone is infected by someone who was detected and ends up in quarantine is going to be 0.5. And the probability that someone is infected by someone detected and ends up in the community or ends up undetected themselves is going to be 0.5 times 0.8. And so each of these we can assign individual probabilities to based on that previous slide with those symbols. And so here's just another way, another visual from our paper that sort of, I think, helps think about what's going on here. And so at generation T, you have some folks in this detected and isolated compartment. And so that in this case, there are 4 people in that compartment. In the Q compartment, we've got 1, 2, 3, 4, 5, 6 people. And in the community compartment, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 people. And so then these individuals, they go on to infect future cases. And so that this intermediate stage indicates kind of how many people they're expected to infect, how many new people they're expected to infect the infections from D. And then in generation T plus 1, this is going to be, so from each of these different compartments, different folks are either detected, and so they end up either in the detected and isolated category, the quarantined, or the community. So in order to calculate, now that we have these pieces, in order to calculate the proportion of infections at time T plus 1, we can take the proportion of infections at time T times the infect matrix times the detect matrix. So that's going to be, in this case, this proportion of infections at time T was 0.2 in the detect compartment, 0.1 in the quarantine compartment, 0.7 in the community compartment, times this infect matrix, which has those effective R values on the diagonal, times this detect matrix that includes these probabilities that we calculated based on those omegas and rhos. And then we're going to go ahead and normalize this to turn it back into a proportion because it's not going to necessarily sum to 1. So we'll normalize this, by which I mean we're going to divide by this proportion of infections at time T. So this DQC is what I'm calling this, the detect, quarantine, and community vector, times the infect matrix. And so we're basically going to multiply these two pieces together and sum the values up and divide by that to be able to normalize this. And so at time T plus 1, we end up with 18% in the detect compartment, 12% in the quarantine compartment, and 70% still out in the community. And so we can calculate from that the effective reproductive number at time T plus 1 by basically multiplying by that infect matrix. And so if we multiply the detect proportion by 2, the quarantine by 1, and the community by 2.5, we end up getting an effective reproductive number of 2.23. And so this basically tells us that we started in the community, we started with an effective reproductive number of 2.5. And so this is basically what we would expect if we weren't doing any testing, tracing, and isolating. We'd expect for, on average, about 2.5 onward transmissions per infection. But now with our test, trace, isolate program, we've been able to lower that to 2.23. And this is malleable based on kind of the values that we gave. So recall that we basically assumed before that our rho, or our probability of detecting an infection in the community, we set that at 0.2. So we said we were just detecting 20% of infections. But maybe in your program, you're detecting more people, so maybe you're detecting 50% of infections. And so we can update all of those 0.2s to 0.5s. And that's going to change our ultimate result. And so we'll do, to calculate the proportion of infections at time t plus 1, we'll still multiply by the proportion of infections at time t times that same infect matrix times our updated detect matrix with our new probabilities. And then, of course, we'll normalize that. And so this results in a pretty different picture. Now we're detecting about 44% of the infections. We're quarantining about 22% of infections, and we've got about 44% still out there in the community. And so now our reproductive number, our effective reproductive number at time t plus 1 is down to 2.1. So we were able to lower that reproductive number from 2.5 to 2.1 based on our test, trace, isolate program.